Hi everyone, let's solve today's daily challenge, that is convert sorted list to binary search tree. In this question, we are given the head of a single linked list and the elements are sorted in ascending order. So we need to convert it into a height balanced binary search tree. Right, so first let's discuss a few things. That is, what is the meaning of a BST? Right, what is a BST? So BST is a binary tree, right? So there is a property that BST, every node in BST should follow. That is, if you consider the root, then the left subtree, all the nodes within the left subtree should have values less than the root. Okay, and all the nodes within the right subtree should have value greater than the root, right? So this is true for each and every node inside of a BST. So this property is followed by a BST, a binary tree which follows this property is called a BST, binary search tree. Right, now another thing that is mentioned in the question is we need to return a height balanced binary search tree. So now you have understood that, okay, so this is the meaning of a BST. So if this is some kind of a list given to you, you can choose any of the nodes from this list, right? And you can try, you can create different kinds of BSTs, because all you have to do is you have to follow this property, right? So if you want to start as -10 as the root node or -3 as the root node, you can do that and you can create a BST. So there can be number of BSTs that you can form from this particular list, right? For example, if you try to create a BST starting from -10, then what will you do? You will try to follow the property. So according to the property, so whatever node we have to insert next, we should see its value, right? If it is greater than the root, we should put it inside of the right subtree. If it is less, then we should put it inside of the left subtree, right? So here you can see -3 is greater, so we'll put it inside of the right subtree. Similarly, 0 is greater, we will put it here. Similarly, 5 is greater. So this is a kind of BST that is formed. Now we can also do the same thing with -3, right? We will say -3 we will take as root node, and what we will do, we see that -10 has value less than -3, so we'll put -10 here as left child, and then we will similar thing, this will be created here, that is 0, then 5, then 9, right? So I hope you are getting, right? So these are both valid BSTs. But another thing that is mentioned in the question is the height balanced tree, right? So what do we mean by height balanced tree? So a height balanced tree, what we do is, if you want to check, whether a tree is balanced or not, we consider the height of the left subtree and the height of the right subtree. So if the tree is balanced, then the difference between the let's call them HL and HR, right? Their difference is less than equal to 1, right? That means this difference can either be 0 or it can be 1, right? So here you see, like, this is a valid BST. If you take -10 as the root node and you create this BST, it is valid. But is it height balanced? No, because if you see the height of the left subtree, HL is 0. And if you see the height of the right subtree, then it is 4. So HR is 4 and HL is 0. So you get 4, right? But 4 is greater than 1, right? So that means this is not height balanced. But if you see the one that is being formed inside of the, first test case, if you check the, okay, let me take a different pen. If you check the height of the left subtree and the height of the right subtree, so the difference is 0, you can see, because it is also 2 and it is also 2. So if the difference is 0, that means we can say that this is a height balanced tree, right? Sometimes what can happen is, let's say this node was not present here, right? We only had, 9 and -3 and -10. Then this is also balanced. Why? Because the difference between the height now becomes 1. So this is also a balanced binary search tree, right? So I hope you have understood what a BST is and what we mean by height balanced, right? Now let's discuss how we will be approaching this question. So if you want, now you know this thing that you can start from any node, right? But if you want the tree to be height balanced, right, what will you do? You will try to get to the mid of the linked list, right? And whatever is at the mid, you will try to make it as the root. Because then what will happen? You will have some values to the left of this mid and some values to the right of this mid, right? So if you consider the mid, then these values will be equal, right? So if you want, if you want to achieve a balanced tree, then definitely you need equal number of nodes in the left, and like ideally equal number of nodes in the left or in the right, or otherwise there can be a difference of one, right? So that is what can happen, right? Here if you would have considered just 4 nodes, then this will be your mid, right? So here you can see the difference is 1, so this is also height balanced, right? So that is what we are going to do, right? So what we will say, what we are going to do is we will be taking the mid of the linked list, and this will be our root node. This will be our root node. And then the elements to the left of this root will become the nodes within the left subtree of the tree that we are forming. And the nodes to the right of this mid will be inside of our right subtree. So basically now we have a linked list here which have 2 nodes -10 and 3. And we have a linked list here which have 2 nodes 5 and 9. So now you can see one thing, that we are trying to create a tree. Now if I treat this like this was the original question given to us. Now if I treat this as the question, I will try to create a tree out of this. So what will that tree look like? That tree will look like this, that is given to you here, -3 and -10, right? So what are you doing? You are choosing a mid value here also. You are choosing a mid value and you are creating a tree. So you see that if what we are trying to do is we are taking a mid and we are again getting 2 different questions, right? 2 valid questions, and we are doing the same procedure on them also, right? So we are again considering a mid, right? If you want to create a tree out of this, you want to create a left subtree now. So that is, you are creating a tree only, right? And you have to follow the same properties, that is, it should be height balanced and it should be a BST, right? So can I say that we can solve this using recursion, right? So definitely I can solve this using recursion. So what we are basically doing is divide and conquer, right? We are dividing this into some sub problems, and then we are doing some operations on that. So we can easily solve this using recursion, right? So what we are doing, we are selecting a mid, and then we know that whatever is to the left will be inside of the left subtree, and whatever is to the right of the mid, that will be in our right subtree. So then we can again make a function call, like first of all we will create this particular node, and then we will link this to this part, right? That you can see here, we will link this to the left child of this node, and we will link this as the right child of this particular node, and we will make a function call to the you will create a function, because we will recursively call this function each and every time for the left part and the right part, right? So that is what we are going to do. So now I hope you have understood what approach we will be taking. So we'll be doing recursion, right? So where we are going to do recursion, first of all we will be calculating a mid, and then we will recursively call function for the left part of the subtree and the right part of the subtree, right? So basically in our let's call it recursion, so we will have the start and end of the linked list, right? So first we will calculate a mid, right, with this linked list, and once we calculate a mid, we get some nodes to the left of it and some nodes to the right of it. So what we will say, we will for the left, right, for the left subtree, we will recursively call this function recur, and we will be starting from the start and to the mid, and then we will call this function for the right subtree also. So we will say mid of right is equal to recur. Okay, it might not be visible here. Let me write it here. Okay, wait. Mid of left, we will be calling this recur function, right, starting from the start of the linked list that we initially had, and up to the mid. Now, because why? Because this particular value will become our end now, right? Then we will be calculating it for the right part. So we'll say recur, and here we will be starting from mid plus 1 and up to the end of this linked list. So we'll consider this part, right? So that is what we have to do. Now let's see how we will be calculating mid. Now you will say, we can calculate this mid by traversing the linked list, right? So first what we will do is we will traverse the linked list, we will calculate its length, and then we will divide it by 2, and then we will again traverse in the linked list and get this particular node, which is the mid, right? But we can do it more optimally, right? So let's see how we can do that. So right now the time complexity of this is what you will be traversing the linked list twice, right? So that is O of n plus O of n by 2, I can say, right? Now let's see how we can reduce this. Although it won't have much of an effect, you can also do it this way, but let's do something which will be even faster than this, right? So what we'll do is we will take a slow pointer and a fast pointer, right? So as we discussed in the when we detect a linked list cycle, right? So we consider these two pointers. So we say that the slow pointer goes by 1 step ahead, and the fast pointer goes by 2 steps ahead, right? So that is what we do. So here we are trying to calculate a mid. So can I say that by the time the fast pointer reaches the end of the linked list, right, because there is no cycle, by the time this fast pointer reaches the end, our slow pointer will be standing at the mid value? Obviously, because fast pointer is traveling twice the speed of slow pointer, right? So here if you try to see, first of all, both of them will be initially at -10, right? Then what will happen? Our slow pointer will move 1 step here and fast pointer will be here. Then what will happen? Our slow pointer will move here and our fast pointer will be here, right? So fast is, after this step, fast will be at null. So basically, how do we check the condition? We check fast pointer as null if it is null, or fast of next if it is null, right? So we check this condition. So here you can see fast of next is null. So that means we have arrived the end of the linked list. So that means wherever we are standing, so you can see clearly here also that the slow pointer is pointing to the mid of the linked list, right? So this concept we will be using. So here you can easily say that we are just traversing n by 2 inside of the linked list to fetch the value of the mid, and we can easily get that. We don't have to do any other iteration. The slow will be standing at the mid value of the linked list. So that is all we have to do. So now let's see it in code, right? Sorry. So here you can see that first of all, so this is our recursive function, right? So first let's discuss here what will be passing. So here first of all, you need to see if the linked list is empty. You need to simply return null pointer. Otherwise you will call this function, right? Inside of this function we need to first value that we pass is the start of the linked list, that is head, and the second value that we pass is the null pointer, right? That is the end of the linked list. Now let's discuss this function. So we already did, but here let's see this part, right? So first of all, we will have start and end of the linked list, right? So we'll check if we only have one node, then we can't do anything, right? Then we will simply return null. Otherwise, what we will do, we will create a slow pointer and a fast pointer. So this is what we are doing for calculating the mid. So as we saw here, to calculate the mid, when we calculate the mid, so slow pointer will be going 1 step ahead and fast pointer will be going 2 steps ahead. So by the time fast pointer reaches null, our slow pointer will be standing at the middle of the linked list, right? So this part will simply return us, so slow pointer will contain the mid of the linked list. So what we will do, we will create a node, right? So whatever is at this slow value, that will become our root for the tree, right? So here we have created the root of the tree, and we have simply put the value inside of this slow pointer inside of our tree, right? Then what we discussed was, okay, I wrote that. All right. So we discussed that now we will be, getting this linked list and this linked list. So we will treat them separately. So when we treat them separately, we will say that we can recursively call this function again to create these subtrees. So what we are doing, we are taking this current node and we are saying that we are linking this, its left, to another recursive call, and we are calling it for start to slow. That is the start to the mid, right? Then we are doing the same thing for creating the right subtree. So we are calling connecting current of right. We are linking this to this right subtree. So the right subtree will be starting from the slow of next, that is from here, and up to the end, right? So up to the end, and then we will simply return current. So by the end of all the recursion, we will be getting the head of this, the root of this tree, right? So that is all we have to do. So I hope you have understood the question. If you have liked the video, please subscribe and also like and share with your friends. Thank you.